Hello everyone and welcome back to Nuclear Reactor Kinetics and Dynamics lectures. In the last lecture we discussed how Laplace transforms can transform a function from the time domain into the S domain. In this lecture we'll discuss how Laplace transforms allow us to solve differential equations with ease and predict the behavior of block diagram control systems. We'll begin with some examples that use Laplace transforms to solve ordinary differential equations. In this example, we will solve the differential equation dy with respect to dt plus 5 times y is equal to some f of t. We'll solve this equation using several different values for f of t, but first we'll see what happens when f of t is equal to a delta function. We also need to specify initial conditions for these equations, and our first initial condition is that y of t is equal to 0 when time t equals 0. We'll start solving our differential equation by taking the Laplace transform of both sides. The Laplace transform of the dy dt term is equal to s times y of s minus y evaluated at t equals 0, which equals 0 due to our boundary condition. The Laplace transform of 5 times y of t is just equal to 5 times y of s, and the Laplace transform of our delta function f of t is equal to 1. We can rearrange terms to find that y of s is equal to 1 divided by s plus 5, and if we refer to our handy-dandy table of Laplace transforms, we see that this means that y of t is equal to e to the negative 5t for all times t greater than or equal to 0. Now this might be a little confusing since our boundary condition states that y at t equals 0 is equal to 0, but our solution function e to the negative 5t evaluated at time equals 0 is equal to 1. This confusion is due to the delta function. The delta function provides a unit impulse just after time t equals 0, which makes our y of t function jump from 0 up to 1 right after the transient starts. Similarly, if our boundary condition had stated that y at t equals 0 is equal to 2, and after we use our Laplace transforms to solve our differential equations, we see that y of s is equal to 3 over s plus 5, and y of t is equal to 3 times e to the negative 5t. So in this case, the unit delta impulse causes our y function to jump by 1 after time t equals 0 from its initial value of 2 up to 3. Now let's make f of t something a little more complicated. Here we'll assume that f of t is equal to e to the negative t, whose Laplace transform is equal to 1 over s plus 1. If we take the Laplace transform of the left side and rearrange terms, we see that y of s is equal to 1 divided by s plus 1 times s plus 5. We can decompose this product into the sum of two fractions, some constant k1 divided by s plus 1 and some constant k2 divided by s plus 5, and we easily see that the inverse Laplace transform of this expression gives us that y of t is equal to k1 times e to the negative t plus k2 times e to the negative 5t. So what are k1 and k2, and how can we consistently find their value when we decompose fractions like 1 over s plus 1 times s plus 5 into their individual fraction components? To do this, we'll use partial fraction expansions. Let's assume that y of s is equal to some polynomial as a function of s, a of s, for example, divided by another polynomial, b of s, where b of s is equal to s minus some root r1 times s minus the root r2, etc. If a does not contain any higher powers of s than b, then we can recast y of s as some constant k1 over s minus r1 plus another constant k2 over s minus r2 plus k3 over s minus r3, etc. We can easily show that any of these ki constants is equal to the limit as s approaches ri of s minus the root ri times y of s. The s minus ri term becomes 0 as s approaches ri, and multiplying y of s by s minus ri causes all the fraction pieces to become 0 once this limit is taken, except for the fraction containing the ki term. So for our problem, we can find k1 by taking the limit as s approaches negative 1 of s plus 1 times 1 over s plus 1 times s plus 5. We see that the s plus 1 terms cancel, and when we evaluate the expression as s approaches minus 1, we see that it's equal to 1/4. Similarly, k2 is equal to the limit as s approaches minus 5 of s plus 5 times 1 over s plus 1 times s plus 5, which, once we evaluate it, is equal to negative 1/4. So after solving for k1 and k2, we see that y of s is equal to 1/4 divided by s plus 1 minus 1/4 divided by s plus 5, and that y of t is equal to 1/4 times e to the negative t minus e to the negative 5t. Now let's consider what happens when f of t is equal to t, which could occur if we have a ramp reactivity insertion, for example. Taking the Laplace transfer of both sides and rearranging terms gives us that y of s is equal to 1 over s squared times s plus 5. If we expand this expression out into its partial fraction components, then we see that's equal to some constant a divided by s squared plus b over s plus another constant c over s plus 5. We can solve for a and c easily. We just do the same exact thing as before. A equals the limit as s approaches 0 of s squared times 1 over s squared times s plus 5, which we see equals 1 over 5. And similarly, c is equal to the limit as s approaches negative 5 of s plus 5 times 1 over s squared times s plus 5, which equals 1 over 25. To determine b, we must take the limit as s approaches 0 of the derivative of s squared times y of s. If we look into what happens to our partial fractions after they're multiplied by s squared, we see that the a term reduces to the constant a, and that the b term reduces to s times the constant b. So by taking the derivative of this expression, our a term, which is just a constant, becomes 0, and our s times b term becomes just the constant b. Our c term remains as something times a power of s, which equals 0 as s approaches 0. So we can determine b by multiplying y of s by s squared, which reduces to 1 over s plus 5, and then by taking its derivative, which equals negative 1 over s plus 5 squared, and then finally by evaluating it as s approaches 0. After doing all this, we see that b is equal to negative 1 over 25. From here, we now have an expression for y of s, which we can convert to y of t. Now let's use Laplace transforms to determine how a proportional control system will behave in response to some input. Here we'll start with a constant unit step input. Our proportional control loop consists of one simple feed-forward element, g1, which is equal to 1 over s plus 1, and a feedback line that feeds the output, c, back into the input signal. We can solve for the system's output, which we find is equal to 1 over s plus 2 times the input signal. We'll first consider a unit step function input, where r is equal to u of t, the Heaviside step function from last lecture, and the Laplace transform of r is equal to 1 over s. This means that our system's output is equal to 1 over s times 1 over s plus 2, which can be decomposed into the partial fractions a over s plus b over s plus 2. We can use our partial fraction approach to solve for both a and b, and we find that our output, c of s, is equal to 1/2 divided by s minus 1/2 divided by s plus 2. When converted to the time domain, we see that our output is 1/2 minus 1/2 times e to the negative 2t. Now let's see how the system would behave in response to a ramp input function. For a ramp input, our r of t signal equals t, and r of s equals 1 over s squared. This means that our output signal, c of s, is equal to 1 over s squared times s plus 2, which can be broken into the partial fractions a over s squared plus b over s plus c over s plus 2. We can find a by taking the limit as s approaches 0 of s squared times c of s, and after the s squared terms cancel, we see that a is equal to 1/2. For b, we take that same s squared times c of s expression, take its derivative, and then take the limit as s approaches 0. After taking this limit, we see that b equals negative 1/4. Lastly, we find c by taking the limit of s plus 2 times c of s as s approaches negative 2, which we see is equal to 1/4. So now we have found the values for a, b, and c, and after we take the inverse Laplace transform of c of s, we find that c of t equals 1/2 times t minus 1/4 plus 1/4 times e to the negative 2t. Lastly, what would happen if our input was a unit impulse represented by this delta function? Since the Laplace transform of our delta function equals 1, c of s is just equal to 1 over s plus 2, which means that c of t equals e to the negative 2t. We notice some consistent behavior for our system for all three of our input function cases. First, we see that the system tends to dampen any input signals it sees. In all three cases, the output, c of t, either approaches 0 as time approaches infinity, or at least the output is less than the input signal, r of t, as it is for the ramp input case. The output signal for the system continues to grow over time, but it grows as a power of 1/2 times t, rather than just t, which is the input, so it grows a little more slowly than the input. Second, we notice that every output signal includes an e to the negative 2t term, regardless of the input signal. In the next lecture, we'll discuss how a characteristic equation of a control system will predict its response, why the characteristic equation of the system guarantees that its responses will contain an e to the negative 2t term, and what the characteristic equation tells us about a system's stability.